This is the third topic of the course, Probability and Stochastic Processes, in which we are going to talk about independence. Suppose we toss two identical coins in different places in the room. Intuitively, because they are tossed in different places in the same room, we expect that both coins will not influence one another. Now, the mathematical concept for this not affecting each other is expressed by independence. We have our definition. Two events A and B are called independent if either the probability of B is equal to 0, of course. Similarly, either if the probability of A is equal to 0, or the probability of A given B is equal to the probability of A. Now, the main definition here is this part. So, this definition basically maintains that the probability of A is not influenced by the occurrence of B, because the probability of A, by assuming first that B happens, is just equal to the probability of A. In other words, A and B are independent if knowing that B happens does not change the probability of event A to happen. Now, the problem is students usually think that disjoint events must be independent. So if we have a Venn diagram of the sample space, for example, sample space S, and inside of this sample space we have two events, let's say A and B, and this A and B are disjoint, namely they don't share any common elements, then students usually think that they are independent. Well, they are independent in the sense of set, but they are not actually independent in the sense of the probability. The opposite is actually true. If A intersection B is equal to the empty set, then knowing that A happens means we know that B cannot happen. So if we know that a particular outcome, omega, is already inside of A, it cannot be inside of B any longer. So these joint events are never independent. They are always dependent upon one another. So be careful about this. Unless, of course, one of them occurs with probability 0. Then, in that case, we will see also with our previous definition. Now, the problem with our previous definition is that it is not actually operational in the sense of if we use it to verify whether two events are independent of one another, it is quite difficult. A more operational definition is therefore required. It is given by the following theorem. Events A and B are called independent even only if the probability of A intersection B is equal to the probability of A multiplied by the probability of B. Now, it is easier to use this as a definition of independence if what we wish to do is just to verify whether A and B are independent. So, if we are given two events A and B and you would like to know whether they are independent, just look whether the probability of A intersection B is equal to the probability of A multiplied by the probability of B. Now, how do we get this alternative formulation? Well, this is actually quite straightforward. We can prove this easily. So originally, the probability two events are called independent if the probability of A intersection B is equal to the probability of A. This is our original definition. On the other hand, we have the definition of conditional probability. Conditional probability says that the probability of A if B is equal to the probability of A intersection B divided by the probability of B. So, if the probability of A given B is equal to the probability of A, that means that we can actually just replace this with this one. Hence, the probability of A intersection B here is simply the multiplication of this one and that one. Okay, now the definition is good right now if we would like to use it to verify whether two events are independent. But independence is not just a tool for us to, it's just something like a fact, but also can be function as an assumption. So we assume independence on the part of the phenomenon that we look at, on the part of the events that we are modeling. Generally, independence is something we assume in modeling a phenomenon. For instance, let A be the event where the result of tossing the first coin is head, and B be the event where the result of tossing the second one is head. If we assume that A and B are independent, then the alternative formulation applies. Namely, so basically, we assume first, and this fact must follow. The probability of A intersection B must be equal to the probability of A multiplied by the probability of B must be equal to 1/4. Of course, you have to be careful that there are many cases where assuming independence has no justification. So when we are modeling something, we have to be sure that independence has justification. For instance, let C be the event where tomorrow is cloudy and R be the event where tomorrow is raining. Let the probability of C is equal to 1/5 and the probability of R is equal to 1/10. If both events are assumed independent, then the probability that tomorrow is cloudy and raining is equal to the probability of C intersection R and equal to the probability of their multiplication equal to 1/5 multiplied by 1/10 equal to 1/50. This is of course wrong because the events are not actually independent. Typically, every rainy day is also a cloudy day. So if you observe that today is rainy, then it is usually preceded by cloudy. Then the probability that tomorrow is cloudy and raining is actually just equal to the probability that tomorrow is raining, namely 1/10. So be careful then in making assumption on independence. Now we have seen the definition of the independence for two events. What if we have more than two events? We have n events. Now events E1, E2 and so forth until En are called mutually independent even only if the probability of any event E1 is not influenced by the occurrence of other events, no matter their configuration. We have the following definition. A set of events E1 until En is mutually independent if for all I inside of 1 until N, so pick any I, and for all S subset of 1 until N but minus I, then the probability of the intersection of Ej, j inside of S is equal to 0, or the probability of Ei is simply the same as the probability of EI given the intersection of all EJ inside of S. So if you see, this definition is actually just the generalization of the original definition. So this part here basically replace, this part here basically replace our probability, that the probability of B is equal to 0, and this part basically just replace the probability that A given B is equal to the probability of A. Namely, take any event EI, the probability of the EI is just the same. Either you assume the other one to happen, the intersection of EJ, J inside of S, and it doesn't matter, it is just the same as the probability of EI. Now this definition is quite involved because you have to take any i's here and then any subset, every possible subset of 1 until n minus I. So if you want to list all of them, it's actually quite complicated, especially if n is quite large. Similarly with the previous definition, we can also obtain another way of defining this. Now if we look at this definition, it is obvious that regardless of which events are occurring, so regardless of this part here is occurring, the probability of event E does not change. For example, if we toss 100 coins in different times, so these are different coins and different time, it makes sense to assume that those tossings are mutually independent, because the probability that the ith coin produces head is equal to 1/2, regardless of the result of other coins. So these coin tossings therefore are mutually independent. Now alternative formulation for this one is given by this theorem, and this is quite more straightforward than the previous definition. A set of events E1 until En is mutually independent even only if for all subset S from 1 until n, for all subset of 1 until n. So right now you don't have to take out the I, it's just take any subset that is possible from 1 until n, then the probability of the intersection of Ej, J inside of S must be equal to the product of all the probability of event J inside of S. So this is also the generalization of the alternative formulation that we have seen before. So the probability of the intersection is simply the product of each probability inside of this set of events. But look carefully that in this definition we are talking about for all subset, for all possible subsets. Now there are many possible subsets of these particular sets from 1 until n. How many of them? Well, because there are n elements inside of it, that means that there are 2 to the power of n possible subsets. But some of them, well, we don't have to check them. So if for example, S here is equal to the empty set, well, we don't have to check it because the intersection of the empty set is just empty set. This product does not apply. So we don't have to check the empty set. Similarly, with singletons. For example, if S here is just a singleton, of course, its probability is just simply its own. So this is just an identity. You don't have to check it. So if we have n events, that means that the number of conditions that we have to check is equal to 2 to the power of n minus 1. And this is very large and grows very fast. for n is equal to, for example, n is equal to 5, we are talking about 32 minus 5 minus 1. But still, this alternative formulation is actually much better than the previous definition for us to verify n events to be mutually independent. An example, if we toss n coins, those tossings are mutually independent even only if for any m element of 1 until n, so take any m, take any part of these numbers and any subset with m coins inside of it, then the probability that all coins inside of that subset produces head is equal to 2 to the power of minus m. So this simply means that we have here S, and inside of this S there are n coins. Take any part of this, and this one has, let's say that this is A. The cardinality of A is equal to m. So the probability that all coins inside of this A produces head at the same time, this simply means 1/2 multiplied by 1/2 and so forth multiplied by 1/2. There are m coins of them, so this is just equal to 1/2 to the power of m, 2 to the power of minus m. Okay, let's continue. Now be careful in making assumptions. So, again, I would like to emphasize this. Making the assumption of independence is something that must be carefully thought. Suppose that in a DNA testing, someone is found to have 5 markers in his DNA, and that according to our research, marker A occurs only once in 100 people, marker B occurs once in 50 people, C once in 40 people, D once in 5 people, and E once in 170 people. Now, if the occurrences of those markers are assumed to be mutually independent, so they don't have any dependence whatsoever, then the probability that someone has the 5 markers simultaneously is equal to, it is basically, according to the previous definition, the probability of A intersection B, intersection C, intersection D, and intersection E is just equal to the product of those probability is equal to the product of 1/100th divided by 1/50th divided by 1/40th divided by 1/5th divided by 170th, and this is equal to 1 divided by 1,000, 170 million. So 170 million. This is a small number in the sense that if you have found that someone have these 5 markers, then it is to find someone else who has the same similar markers will happen with this probability, and this is a very small probability. That means that if you do this in random, then the probability of finding someone with these markers simultaneously is given by this probability 1 in 170 million. Now, the definition of mutual independence that we have seen looks highly complex and involves many conditions. Like previously, I have already explained that the number of conditions also grows exponentially, 2 to the power of n minus 1. The number of subsets we must inspect is very large and grows very fast. The following example illustrates this. Suppose we toss 3 fair and mutually independent coins. So these three coins are mutually independent, so their tossing is also mutually independent, and furthermore, they are fair. What does it mean to be fair? Well, it means that the probability of one particular coin producing head and tail are equal. And then we define the following three events. A1, event where the result of the first and the second coins are the same. A2, the event where the result of the second and third coins are the same. And A3, the event where the results of the third and the first coins are the same. The question is, are events A1, A2, and A3 mutually independent? Now let's look. Because we have three coins, then and the result that is produced by these three coins are basically the quantities, the randomly determined quantities. So we can model this simply by assuming we have a sequence that consists of three components, namely the result of the first coin, the second coin, and the third coin. And the result of each coin is of course only consists of either head or tail. So when you perform a particular experiment, all you have to do is assigning this value, this possible value, to each one of these components, and then we have our outcomes. Therefore, the sample space of the experiment is just this set, namely H, H, H. Here means that the first coin produces head, the second one also produces head, and the third one produces head, and similarly with the other. There are 8 possible outcomes. Now, each of these outcomes has probability 1/2 to the power of 3, which is equal to 1/8. Why is that? Because each of these coins are assumed to be fair and mutually independent. Therefore, the probability of each event is, let's look at the event right now. Event A, A1, happens when the result of the first coin and the second coin are the same. When does it happen? Well, it happens in these outcome, for example. Also in this outcome, also in this outcome, look at this. So both produces tail, and also in this outcome. So therefore, the probability of A1 is equal to the probability of this set of outcomes, and if you sum them all together, it produces 1/8 plus 1/8 plus 1/8 plus 1/8 is equal to 1/2. In a similar fashion, we can also compute the probability of A2 and the probability of A3, and both also produces 1/2. Now, to determine whether A1, A2, and A3 are mutually independent, we can use the mutual independence theorem that we have seen before. We have seen that the probability of A1 is equal to the probability of A2 equal to the probability of A3, which is equal to 1/2. So what we are going to do next is to see the intersection of two events. Let's look first the probability of A1 intersection A2. Well, A1 and A2, so let me return again to the previous slide. So if you see here, A1 consisting of this set. Now let's look for A2. A2 consists of, well, this happens when the second and the third coins produce the same. So the second and the third, this happens for this outcome, for this outcome, yeah, and then also for this outcome and for this outcome. So we have H, 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 and then H, T, T, and then T, H, H, and then T, T, T. So this is A2. Now, the intersection between A1 and A2 therefore includes these outcomes. Okay, so the intersection contains H, 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 and T, T, T. Therefore, the probability is equal to 1. 8 plus 1, 8, 1/4. And this is also equal to the probability of A1 multiplied by the probability of A2, namely 1/2 multiplied by 1/2. So they are the same. This is good. This is good because we have just verified the condition. We can also compute the probability of A1 intersection A3 and the probability of A2 intersection A3 in a similar fashion. However, we still have one more condition, namely the intersection of the three events. Now, the probability of A1 intersection A2 intersection A3. So if you see their intersection, the intersection of the three of them is this set. So the intersection of the three of them contains these two outcomes, namely H, 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 and T, T, T. So the probability is equal to 1/4. But the product of these three probabilities, the probability of A1 multiplied by the probability of A2 multiplied by the probability of A3, this is equal to 1/2 to the power of 3, which is equal to 1/8. So therefore the probability of the intersection between A1, A2, and A3 is not equal to the product of the probability of A1 with probability of A2 and probability of A3. Therefore, the three events are not mutually independent because the condition says that for all subsets, even though any two events among them are mutually independent. Now, independence for just any two events is called pairwise independence. And we can generalize this pairwise independence. A set of events A1, A2, A3, and so forth is called k-way independent even only if any subset containing k elements is mutually independent. Remember, any subset containing k elements is mutually independent. So inside of these k elements, they must be mutually independent. The set is called pairwise independent even only if it is two-way independent. Now this definition is better than the previous one in the sense that we only deal with smaller number of conditions to check. So how many number of conditions do we have to check? Well, because we are talking about k elements, then the number of conditions that we have to check is equal to 2 to the power of k minus k minus 1, which can be really smaller compared to 2 to the power of n minus 1 if k is smaller than n. For instance, take k is just 3, for example, while if you have n, the number of set inside of the number of events inside of this set, maybe 10, maybe 100, for example, and this is really smaller than the number than if we have to insist on mutual independence. Now the previous example is not mutually independent but pairwise independent because any two events are mutually independent. But three-way independence means that it is not simply that any three events. Yeah? It simply means that any three events are mutually independent. But it does not mean that if you take any three events, then the probability of the intersection of these three events must be equal to the probability of their the product of their probabilities. It is not only that, you have to check also the configuration when we have two events inside of it. Yeah, remember that these k elements must be mutually independent. Pairwise independence, therefore, is a much weaker condition compared to mutual independence. Now let's continue with our previous example. So suppose those previous markers that we have only occur with pairwise independence. What happens then? Then the probability of A intersection B, intersection C, intersection D, intersections E must be limited by the smallest probability of two events occur at the same time. And the smallest probability, yeah, happens when event A and event E happens, because the smallest probability, well, the smallest one is the probability of event E to happen, namely 1/170, and the probability of event A to happen, namely 1/100th. So this must be bound by the probability of A intersection E, namely the probability of A multiplied by the probability of E, 100th multiplied by 170th, which is equal to 1 divided by 17,000. And this is, of course, is way smaller than the previous one. What if there is no independence at all? Namely, these five markers are actually dependent upon one another. For example, anyone with marker E also has marker A. Anyone with marker A also has marker B, and so forth. So this simply means that if you have any marker, then also you have the other markers. But in this case, the probability that someone has the five markers simultaneously is simply the smallest probability among them, namely the probability of E, which is equal to 1 divided by 170. And this is also way larger probability than the previous one. So which one of these are the truth? Of course, it depends on the phenomenon that we look in real life, but we have to be careful. Now these markers, for example, let's say that E marker happens with probability 1 divided by 170. And we see that if we collect 170 people, we expect only one of them to have them. But if we assume that these markers are independent of each other, then the probability of someone to have these five markers simultaneously is really, really small. This is the end of the third topics of the course, probability and stochastic processes. Thank you.